for methane coupling. The speaker is Barbara Warren.
Thank you very much for the introduction. I would like to thank John Stencil and the officers of the Tri-State Catalyst Club for inviting me to participate in this symposium today. The title of my talk is Exploring and Avoiding the Homogeneous-Heterogeneous Mechanism for Methane Coupling. And Union Carbide has been pursuing a program jointly sponsored by the US DOE, Pepsi out of Pittsburgh, and the Industrial Chemicals Division, and we appreciate the support we have received from the DOE for the work, which I'll talk about today. I'm only going to be talking about a part of the work which was done in this contract. And although there is no need for me to mention this, it is very important to find an economical process for the conversion of methane to ethylene for the future, because currently it's either flared or injected, and this situation should change in the future. Union Carbide has a particular interest in ethylene. The DOE has a particular interest in fuels, so we have been studying the conversion of methane to ethylene. Our interest is in producing ethylene, and in fact, let me see. And in fact, this reaction has been reported with a number of catalyst systems, and the mechanism presented in this slide is Jack Lunsford's mechanism for a variety of solid materials for the conversion of methane to ethylene, which is a reaction which is conducted at very high temperatures, between usually 750 and 900 degrees centigrade, and generally close to atmospheric pressure. It involves the extraction of hydrogen from methane from an activated oxygen on the catalyst to produce a methyl radical, which is then released from the catalyst surface into the gas phase, where two methyl radicals couple to form ethane. Ethane is subsequently converted to ethylene by well-known homogeneous reactions in the gas phase. The important thing is that for a variety of different catalysts, the product distributions observed from these reactions are generally the same, which indicates that the product distribution is largely dictated by the gas phase chemistry, which if you look into combustion chemistry, homogeneous chemistry at high temperatures, is the chemistry that we're talking about. When Jack first proposed this mechanism, many people didn't like the idea of a mechanism which involved both a heterogeneous component and a homogeneous component, but it has been shown in many other researchers' work that this is probably a correct mechanism, i.e. you have a contribution from the catalyst and you also have a contribution from the gas phase chemistry. We began our research with a very, very simple catalyst system discovered but not reported by George Keller and Madan Basin in 1969. They were studying redox metals on alumina, and in fact also ran some non-redox metals, and one they ran, sodium chloride, showed surprisingly high C2 yields. We subsequently ran this catalyst under co-oxidation conditions, and all of the work I'll be talking about today will involve 10% methane, 5% oxygen with balanced nitrogen. If you in fact run the sodium chloride alumina catalyst under these conditions, what you find is that it rapidly deactivates. But initially, you have C2 yields and you have selectivities which are comparable to many of the reported literature catalysts. You can see here the rapid catalyst deactivation, and we thought, well, let's see if that's due to the loss of chloride. At the time that we began this work, in 1987, there were very few systems in the literature which had used chloride, but it was those systems in the literature which, if you look carefully, had high ethylene to ethane ratios. We were very interested in a high ethylene to ethane ratio in the oxidation of methane, because ethylene was the product we were interested in. If you add 500 parts per million ethyl chloride to the deactivated sodium chloride aluminum catalyst, you retain part of the catalytic activity, but not all of it, and after that you see catalyst deactivation. If you then, after 24 hours, examine your catalyst, you find it's lost nearly all of its sodium. If you look at cesium chloride, rubidium chloride, potassium chloride, the other alkali chlorides on aluminum or on other supports, you find also that they rapidly lose the alkali component. The chlorides are very volatile under these conditions. Therefore, we went to less volatile compounds. We went to alkaline earth compounds. Now here you see also that initially you have C2 yields between 15 and 20%. Selectivities are not particularly high in this example, but you'll see some other examples in which they are high with the alkaline earth salts. So what you see is that after deactivation, if you add 500 parts per million ethyl chloride to your catalyst, you do retain more of the activity than you did with the alkali chlorides. And in fact, the deactivation is not nearly as rapid afterwards. This looked promising, and we continued studies of the alkaline earth chloride salts and found a class of catalysts which were entirely competitive with the literature catalysts and in fact were stable, which is unusual. You'll find that in the literature there are very few, in fact there are no reports of catalysts which are stable for hundreds of hours with reasonable C2 yields. This class of catalysts contain alkaline earth components, chlorides, and what we call a metal oxide combustion promoter. A metal oxide combustion promoter is a metal oxide which without promoters would burn methane. So normally, and in fact if you look at the early methane coupling literature, for instance by Professor Behrens, you will see that he suggests, and other groups, including the group at Grace, suggested that a basic support was necessary for good selectivities methane coupling catalysts. In fact, we were surprised to find that this was not the case. The first support we used, which was a alpha alumina, Norton 5451 alpha alumina, it's not very acidic, but it is not particularly a basic support. And in fact, titanium, zirconium, gallium, aluminum oxides, and some of the more acidic aluminum oxides turned out to be the best supports for high selectivity, high yield, and stability of the catalyst. The best supports are acidic, and in fact, depending on the support, you have a different requirement for the level of chloride you feed to the catalyst. And this is actually quite interesting. The basic supports do in fact burn methane. For instance, magnesium oxide alone would burn methane. Relatively unselectively, you get carbon dioxide, carbon monoxide, but in fact, you don't get the high ethylene-ethane ratios with the basic supports at all that we were interested in. Now, when I said that you require a different amount of chloride for the different metal oxide combustion promoters, here's an example on titanium with barium carbonate. If in fact you feed 6 parts per million ethyl chloride from the beginning of this reaction for over 100 hours, you see the catalyst will not activate. Very poor selectivity and activity. Selectivity is blue, C2 yield for your reference is red, methane conversion is black. Upon addition of 500 parts per million of ethyl chloride, you see the activity jump up, methane conversion nearly 30%, C2 yield close to 20%, and the selectivity jumps up to 60%. And in fact, that will continue undisturbed if you leave 500 parts per million for hundreds of hours. On the other hand, and we had fun testing these catalysts because you actually have to test each one at a variety of levels to find out which combination would be good. Here you see the opposite effect. You see at 10 parts per million, you activate slowly. In fact, the first 2 points are at a different space velocity, but you activate slowly using barium carbonate on alpha alumina, and you have reasonable C2 yields here in this case. But if you add 500 parts per million ethyl chloride, you deactivate very rapidly. You do see the selectivity go up at the lower conversions, but eventually it also would die with the high chloride. You're poisoning your catalyst. This is just the opposite requirements from the titanium. I think that there are 2 things to notice here. There is an activation when you start with barium carbonate on aluminum. The C2 yield increases due to the addition of chloride to the catalyst. I'll refer to that later. If you use a basic support, magnesium oxide, zinc oxide, and the acidities were measured by irreversible ammonia absorption, what you see is under all conditions, and we tested many conditions including lower space velocities, at temperatures below 760 degrees, and we ran almost everything at 750 below, everything. The ethylene to ethane ratio, which I've abbreviated over here by the equal sign over the dash, is 1.6. We never obtained a lined out catalyst on a basic catalyst with higher ethylene to ethane ratios than 2. With Norton 5451 aluminum, which is not particularly acidic, but not particularly basic, we can get ratios of over 2. Titanium, after running for 90 or 100 hours, your ethylene to ethane ratio is 10. So with the basic supports, we never got high ethylene to ethane ratios. Here's an example that shows you from the startup of a reaction the rate of formation of blue carbon dioxide, red is ethylene, black is carbon monoxide, and green is ethane. So when we start with this catalyst, what you see is for 100-hour, hundreds of hours, you see that the rate to CO2 drops. Slow change, slow catalyst change. You see initially a rise in the rate to CO, ethylene, and ethane. And in fact, upon changing the level higher of chloride, you always see not only an increase if you're below the optimum level in the rate to C2s, but a drastic increase in the ethylene to ethane ratio. So the increase in the rate to ethylene is greater than that to ethane. So what does this mean? Here's another piece of information, and here we are increasing the ethyl chloride ratio, which is red. This is the rate of formation of ethane, and the rate of formation, of ethane is green and ethylene is red. We also have shown the effect of the addition of ethyl bromide in this case. And what you see is that you increase drastically, increasing the halides, the rate of formation of ethylene, whereas the rate of formation of ethane remains the same. Now, you remember that the mechanism which has been proposed is that you create your ethane by coupling of methyl radicals. So what we think the evidence shows, and if you change the ethyl chloride, there's a very, very fast change. We think it's simply the gas phase conversion of ethane to ethylene, which is well precedented with chlorine radicals in the gas phase. So we think that the ethylene to ethane ratio depends on the gas phase concentration of chloride radicals. If in fact Harold Kuhn reported a procedure recently for measuring the enhancement in the gas phase reaction from surface radicals kicked off of the catalyst. As you know, Jack Lunsford has this Miser apparatus which he and Ken Campbell reported and measured the rates of methyl radical formation and correlated that with the rates of reaction. But for alkanes higher than methyl, you cannot do that. You can do allo, but they simply are not stable enough. They have other options. So what happens? Harold was concerned with butane oxidation, and he wanted to know whether or not he was releasing butane radicals from the catalyst surface. So what he did was, he made a catalyst bed, put a void space before and after the catalyst bed, with the reasoning that if you had a homogeneous component to the reaction, and you ran with two reactions simultaneously, the one with the void space after the catalyst bed would show enhanced rates to products created in the gas phase if you kicked radicals into gas phase. So we used his techniques here. Reactor number 2 is the one with the void space after the catalyst. Reactor number 1 is the void space before. And if you run control studies, you see that methane conversion increases by less than 1% if you just have a void space without a catalyst. That's not a problem. So what you see is CO, which is the blue pluses here. In each set of a variety of conditions, CO is produced at a higher rate in the reactor that has the void space after the reactor, meaning there is increased gas phase contribution to this reaction. Here, under all conditions. On the other hand, and we do know from combustion chemistry that CO is the primary product of the oxidation of alkanes, If you look at the CO2 rate of formation, it's the same. Under the same set of process conditions, under all cases, the blue markers are on top of the red circles, which confirms our thought that CO2, or this is consistent with the observation or the proposal that CO2 is formed by catalytic reactions, surface reactions. Therefore, the alkanes and or CO are oxidizing on the catalyst surface, whereas CO is largely formed by the reaction in the gas phase. Likewise, in the same reaction, the blue circles represent formation of ethylene. The blue reaction is ethylene. The blue reaction is reactor number 2 with the void space after the catalyst bed, where you would expect to see enhancement from the catalyst released into the gas phase. You see a higher rate in each case of ethylene formation where you have the void space after the catalyst, and a lower rate of ethane. So it looks as if what you're doing indeed, methane conversions are similar in these cases. They're a little bit increased with a void space after the reaction. So you're converting ethane to ethylene in the gas phase, which is consistent with the other information that we see. So what's the role of chloride? What have we seen? One thing we've seen is that you increase the amount of the homogeneous reactions with chlorine. We see the overall rates are slightly larger. Higher ethylene to ethane ratios, we believe, from a gas phase reaction. Increased CO, which you'd expect if you increase the overall chain reactions in the gas phase, same amounts of CO2. So we think chlorine radicals are produced on the catalyst, released into the gas phase where chain reactions occur, in a manner similar to what has been proposed by Jack Lunsford for the methyl radicals. That is not the only function of chloride. The other two functions, in addition to the higher ethylene to ethane ratios, you see that if you start with the chloride, a catalyst devoid of chloride, add chloride, you see the increased rate to C2s. We think the higher activities from conversion of stable salts, for instance, aluminates, titanates, carbonates, to a species, to an alkali species, which contains an active oxygen. So we think what you do is you tend to deactivate most of the catalysts in the literature by converting them to stable salts. And the parts per million of chloride basically destabilizes these salts and catalyzes their conversion to the active oxygen compound. The higher selectivities, the slow change over hundreds of hours, we think is some kind of poisoning, selective poisoning of CO2 formation on the catalyst, which is interesting. But in spite of all of this, and here are some examples. Here's one starting with hydroxide. It doesn't matter particularly which anion you start with. You can probably end up with a common mixture of anions if you start with nitrate or hydroxide or chloride or carbonate. However, using different alkali cations and anions, you end up with different dispersions. So if you look by microscopy, EDX backscattering, what you see is the chlorides don't end up with the higher dispersions as the carbonates, hydroxides, and the other components. So if you start with a chloride at the beginning and the end of the reaction, you have clumps of the alkalis on your catalyst. If you start with the carbonate, barium carbonate, you have a fairly good dispersion to begin with. And if you chop your catalyst pellets in two, you see that it migrates and disperses throughout the catalyst during the reaction. We don't really understand why the chlorides are so bad. Here's another example, and you can see that the rates are essentially identical. This is starting with the carbonate. You have higher than 60% selectivity, close to 18 to 20% C2 yield, about a 5 ethylene to ethane ratio in this case. 30% methane conversion. We can run as high as 400 hours, which is as long as we wanted to run. So where are we at this point? The little green boxes here are the literature catalysts, many literature catalysts, which are plotted results. The bigger blue boxes are results from these alkaline earth chloride metal oxide catalysts. This blue line at the bottom is 30% yield. The yellow line is the 40% yield from methane to C2s, and this star here is what our engineers have calculated that using this process or a similar process would be required in fourth quarter 1989 dollars on Texas from ground up. Now what this says is that none of the literature catalysts, all of which we believe use this heterogeneous, homogeneous mechanism, are suitable for commercialization. commercialization now or in the near future, unless things should change drastically. So what do you want to do? You have a choice. You can either give up, you can hope for a drastic change, or you can look for a different mechanism. At best, if you look at the heterogeneous homogeneous mechanism, if you look at the S.I. Phillips model, you might predict, you might get 59%. You might predict 59% yields at selectivities approaching 80%. In fact, you can see that there are transients up to 30%. Practically, you can't run anything stable over 22%. So we like to get away from the gas phase chemistry, and there are two things we can do. We can either go more to a surface reaction, or we can drastically alter the gas phase chemistry. So use one or the other extremes of this heterogeneous homogeneous mechanism. How do we do this? Well, everybody probably locked in on that article by Otsuka where barium peroxide was shown to convert stoichiometrically methane to C2s at 400 degrees and below, sodium peroxide as well. Certain metals activate hydrocarbons unselectively at low temperatures, the favorite one, of course, being silver, or in fact there are other metals. And everybody knows silver can be modified to allow selective oxidations because of the ethylene oxide reaction. So we were hoping that we could take something which was active at low temperatures, modify it, and make it selective for the formation of C2s. Get away from the common mechanism. 425 degrees silver on alpha alumina, you make it like you make an ethylene oxide catalyst, shows complete oxygen conversion, 25% methane conversion. If in fact you add barium chloride to this, you have a 10% C2 yield at 650 degrees, and we've never seen that kind of C2 yield with any of the literature catalysts in our laboratories. And incidentally, the lithium mag-ox catalyst, we've been able to repeat their results. 700 to 720 degrees, we can get 20% C2 yields, but it does deactivate under these co-oxidation conditions, 12% in 50 hours. At 670 degrees, we didn't see quite as high. This is a different catalyst with a smaller amount of silver and prepared by a different mechanism. But in this case, we have extremely high C3 amounts, comparable to the amounts of C2s. They're all propane. And Kim Campbell is studying some other catalysts, a different system, and notice this and the significance of this, which is in the methane oxidation reaction, your C3s are largely propylene. It has been shown that this largely occurs through addition of methyl radical to ethylene in the gas phase. If you see no propylene, we do not have the same mechanism as the heterogeneous homogeneous mechanism of all of the rest of the catalysts. We see only propane on these catalysts at low temperature, which indicates that we have in fact avoided the heterogeneous homogeneous mechanism. As soon as you would kick off an ethane, you'd be into the ethane to ethylene, methyl radical plus ethylene regime, you'd see some propylene. So you almost have to propose you have methyl radical coupling on the catalyst, followed by abstraction of hydrogen producing an ethyl radical, which then combines with the methyl radical to produce the propane produced. So this is a very interesting leap. All right, what about the other approach? Change the mechanism. Change the vapor phase mechanism. Let's take cesium. Let's oxidize it in the gas phase. Put a volatile complex in the gas phase and jack it all the way up to cesium hydroperoxide. Have the hydroperoxide in the gas phase, extract the hydrogen from methane, and then what do you have? You have a methyl radical, which unlike a catalyst surface, if you create a methyl radical on the catalyst surface, you have a huge pool of oxygen, which can then compete and further oxidize. In the gas phase, you don't have that huge pool on the one complex. So hopefully you have a chance of selectively oxidizing or producing methyl radicals. So we have a quartz tube with a cup. In the top, we put our catalyst, which is volatile metal complex in the top. We have one oven here with a vaporizer temperature, a second oven below. And our methane comes in around the edge of the second tube in the first one and joins with the oxygen in the hot region with the mixture of oxygen and nitrogen containing our volatile metal chloride. And what we see is not what we expect. No, we did not selectively convert methane to C2s. But we had a background reaction in this large void volume of the reactor of 5% at 650 degrees before we heated that cup containing the cesium chloride. And when we heated it, all of a sudden, we didn't make our CO anymore, carbon monoxide. So, at higher temperature, we have, in the presence of cesium chloride, 4% conversion. We lower the temperature of the vaporizer, and we see that, in fact, it goes back up. So what you've done is, by adding parts per million of cesium chloride to the reaction, you've selectively turned off the burning of methane CO. So we did it in the presence of a catalyst. And indeed, it does. The methane conversion is about the same when we add the cesium chloride when this oven is hot. Methane conversion is similar. Selectivity to C2s goes up, you cut out the formation of CO. That methane, which would have been converted to CO, is now converted to C2s on the catalyst surface. This is not optimized. We weren't set up to run the optimized reaction in that particular reaction. But this also is a good lead that shows that you can alter the vapor phase chemistry. So that's an approach. And in summary, we have some stable catalysts. They're competitive with the literature catalysts, but they're not good enough to commercialize. We do have catalysts which give us high ethylene to ethane ratios, which we saw. We have demonstrated two concepts, enhanced surface reaction and changed vapor phase reaction, which we think might be of interest for the future generations of methane coupling catalysts. Although we certainly think commercialization is years away, 10 to 15 years away, and will require technical breakthrough. I would like to thank the surface analyses done by my co-workers, Razi Sayed-Monir, Molly Busby, and Phil Page, and acknowledge the technician who carried out these runs, Richard Chafin, and the contributions from Ken Campbell, who is here today. Ken had many discussions which were helpful in insights into the methane coupling research and allowed me to use his computerized database and his knowledge of the literature. I'd like to also mention that Ken Campbell has also been working for 2 years on methane coupling